In this lecture, I will explain the flow in pipes and ducts. These flows are internal flows, like the gas flow inside a gas transmission line, the liquid pumping system, the HVAC system, biomedical flows, and biological systems. The flow inside the pipe or duct is either laminar or turbulent flow. The laminar flow is streamlined, like you can see in this figure. The flow is moving along a straight line. As the inlet velocity is increased, the flow becomes chaotic and turbulent. This die shows us the chaotic behavior of fluid particles moving inside a pipe. An important flow parameter that is to be defined is called Reynolds number. Reynolds number is the ratio of inertial forces to the viscous forces. Inertial forces are due to the velocity of the moving fluid, and viscous forces are due to the friction inside fluid. The Reynolds number at which the flow becomes turbulent is called critical Reynolds number. Up to 2300 value, the flow remains laminar, and between 2300 to 4000 Reynolds number, the flow is transitional flow. And beyond the 4000 value, the flow becomes fully turbulent. For non-circular ducts, like in the HVAC systems, we use hydraulic diameter instead of diameter. The hydraulic diameter is the ratio of cross-sectional area to the perimeter. For a circular pipe, the hydraulic diameter is equal to the diameter of pipe. For a square duct, the hydraulic diameter is equal to the length of any side. And for rectangular duct, hydraulic diameter is equal to 2AB divided by A plus B. Now I will explain the velocity boundary layer. As we can see in this figure, the velocity is 0 at the wall, and it increases as we move away from the wall, and it reaches a maximum value at the pipe center line. This is due to the viscous forces between the fluid layers, which tends to stop the fluids and reduce its velocity in return. As we can see in this figure, the thickness of the boundary layer is increasing as the fluid is moving forward inside a pipe, and delta is representing the thickness of this velocity boundary layer. This thickness reaches its maximum at the pipe center line, where two boundary layers meet each other. This is the point where we enters the fully developed region. In boundary layer, the effect of viscous shearing forces are prominent, which opposes the fluid motion. So they are friction forces or drag forces. Now we will differentiate between the entrance region and the fully developed region. Entrance region is the region from pipe inlet to the point at which the boundary layer merges at the center line, and viscous effects are seen across the pipe. So beyond this point, the viscous effects are throughout the pipe cross section, where this blue shaded region is the inviscid flow region, where viscous effects are negligible. The fully developed region is the region in which the velocity profile is fully developed and it does not change. The entrance region length can be found by this empirical relation, and this entrance region length is a function of Reynolds number and pipe diameter. This parabolic curve is the velocity profile, and it is expressed by this expression of UR. This expression is for the velocity profile for laminar pipe flow. In this expression, if we put in the value of this small r equal to 0, that means we are at the center line, we will get the maximum velocity. And if we put the value of this small r equal to capital R, that means we are at the wall, and at the wall we will get the velocity equal to 0. Wall shear stress is denoted by tau W, and it is the opposing force or friction force that is offered to the fluid flow by the wall. So Wall shear stress at the pipe wall is related to the slope of the velocity profile at the surface. Mathematically, tau W is equal to mu partial u over partial y at y is equal to 0. That means slope, this is the slope of velocity at the surface multiplied by this constant, which is mu viscosity. The wall shear stress is maximum at the pipe inlet and it decreases as the fluid moves forward in the pipe, but it becomes constant in the fully developed region. In piping system design, pressure drop measurement is very important. With the help of this pressure drop measurement, we can select a suitable pump for the pumping of fluid inside a piping system. The pressure drop in a pipe having length L and diameter D can be found by this pressure drop expression. In this expression, the F is Darcy friction factor, and this friction factor for laminar flows can be found by this expression. For turbulent flows, this Darcy friction factor can be found by Moody's chart, or we have some empirical relations that will be discussed later in the coming lecture. Also, with the help of this pressure drop equation, we can find out the head loss. Head loss is equal to pressure drop divided by rho g. This expression of pressure drop is valid for laminar and turbulent flows, for pipes having smooth or rough surfaces, and pipes with circular cross-section and non-circular cross-section. With the help of pressure drop, we can find the average velocity for laminar flow in a horizontal pipe. This average velocity is a function of pressure drop, pipe diameter, and length of the pipe. We can also find the volume flow rate with the help of average velocity, which is the product of average velocity and area of cross-section. The relation of volume flow rate with the pressure drop and diameter and length of the pipe is called Poiseuille's law. For laminar flow in inclined pipes, we can find the average velocity and volume flow rate by using these expressions. In this expression, a term that has been added, that is rho gl sine theta. This term is added due to the weight of the fluid. This weight is added when the fluid is moving uphill, and this weight is subtracted when the fluid is moving downhill. These expression of average velocity and volume flow rate will be used when we are given the pressure drop data for laminar pipe flow. Thank you for watching this video. In the next lecture, I will explain the turbulent pipe flow.